the rational fractional Laplacian. So I will introduce in the next slides so the object, but still just to say that this is a very hot topic, and there are several open problems that I will tell about. And it's interesting because it provides somehow natural limits for the classical Laplacian and for classical elliptic regularity theory. And I think it is important to study these questions, not only for applications, but also for the analytic point of view. What is important and interesting to see here is that, in fact, many arguments that are used in the classical world cannot work anymore, and somehow one has to redefine things and somehow to find out new ideas in order to overcome certain difficulties that are involved in this problem. Let me just introduce quickly the first object of study, which is made the fractional Laplacian that maybe many of you know. Which is an integral operator, and it is non-local in a sense. If you look at maybe even if you have a function w, which is compactly supported, so you know that just looking at the integral equation, so the fractional Laplacian, when it acts on w, this function does not necessarily have a compact support. So which means you cannot only local information cannot tell you much on this operator. And maybe this is a PV integral, so the PV integral is defined as a limit, and maybe I think some of you knows also this, but we can discuss this. Anyone who have questions can just stop me because it is a lecture, and since it's online, maybe with slides, but we cannot write everything. So please stop me and ask questions anytime. So the constant, so that is in front of this, which is a constant that simply tells about when when we look at the Fourier transform of this operator. In this case, we have a nice formula. We will come back to this later on. And in fact, using Fourier transform or exactly these integral equations with this term, so we can see with the gamma function to the 1 minus s. So if s is converging to 1 also, so we recover the fractional Laplacian. So we recover the fractional Laplacian. So this is something that is important, and somehow this operator provides a limit for the classical Laplacian. So the next here now is what is somehow known as the regional fractional Laplacian, or somehow the omega regional fractional Laplacian. So maybe if you look at here also, we see that nothing changes, so except that the domain of integration is now regional. It's not on the whole space, but it's regional. So this is the reason why we call the name of regional. So in a sense, if you look at the process for the fractional Laplacian, so you have a Levy process. It's generated by a Levy's process, which is symmetric, stable. But for the regional fractional Laplacian, it is generated by a process, which is obtained, of course, from the one of the fractional Laplacian. But still, that Levy process is not symmetric. But still, it is an interesting process because it allows somehow to understand particles that are sensory to jump outside omega. So this is the ratio. This is the reason why the probabilistic colleagues they call it sensory fractional Laplacian, or maybe sensory process, because the process is somehow sensory to jump outside the domain omega. And in that case, we can somehow define different problems in the case when we are interested in phenomenon in which we have particles that should not allow that are not allowed to jump outside omega, but are killed on the boundary or reflected when they reach the boundary. And in the Brownian case, we all know that these are just the kind of Dirichlet condition and Neumann condition. And so let me just go on directly to those definitions. So I will start maybe perhaps with elementary things that, but maybe just to introduce the notion that we want to introduce. So let me just okay, so this is the aim. So sorry. So this is the aim of the lecture, is to give an overview of the boundary regularity. So for this problem that I just mentioned before, so boundary regularity for problems involving the rational fractional Laplacian, and where in the case where we have Dirichlet or Neumann boundary condition. So in a sense, in the situation where we have killed the process when they reach the boundary or reflected. So in the Brownian case, this is well known, and introduce that I just to consider so omega an open elliptic set, and I think maybe many of you are already familiar with these spaces. And I introduced the Sobolev spaces H1 and the H10 space. And so which is just the space of function in H1 such that so U is 0 at the boundary. And in this case, so one is interested in the most famous problems, the simple problems, which are just in the Dirichlet problem, which is just a weak solution for the Laplacian with a solution which are 0 at the boundary. So these are somehow call it the operator that comes with the Dirichlet boundary conditions comes with just when you kill Brownian motion at the boundary, which is very possible. But in the case of the fractional Laplacian, we will see that later on. In some cases, the process may not even touch the boundary, and so this is also a feature that we will see later on. And in the reflected case, this is the usual Neumann problem, where we have the fractional, we have the Laplacian of U equal F, but U is in H1. So in a sense, in 3, so we have a few test functions compared to 4, but still in this situation, we will see that the solutions they have, they do not have any problem in terms of boundary regularity. But this will not be the case when we consider the Levy process, and we will see later on that these two problems will be very different in fact. Okay, so just to consider simply so the weak formulation of these problems, which are well known. So somehow here, so the main difference is that in fact one is just considering different test functions, and somehow we in the Neumann case, one is looking at functions which are continuous and smooth up to the boundary. Well, sometimes you can remove C infinity C, the C can be removed, of course. But, yeah, so, well. And this is just to allow a lot of to obtain a free boundary on U. So you do not we do not restrict any we do not prescribe any boundary condition on U, and this will bring a kind of free boundary, so which is a Neumann derivative. But V in the case of the Brownian motion, or maybe the Dirichlet problem, one sees that the boundary condition is already in the space. And somehow, the simplest and somehow here the important point here that one always consider is the Gauss-Green formula, so which allows to say that if you have a classical solution, then if you have a classical solution, then you can make your integration by parts, and then your weak solutions will become classical solutions. And this would give somehow that the solution of the equation that you are looking for in a pointwise sense. But then the question that comes is clear now. So from weak solutions, can you prove that your solution is regular enough to become classical? And also, what can you see at the boundary that allows you also to make a full integration by parts, so that your weak solution will be a classical solution and solve the equation that you want. So I will just tell the classical results for the local operators. So the restriction on the test functions, if you look at this, we see immediately that from the Gauss-Green formula, if I have a classical solution, then with the restriction on the space of test functions, then I will have just simply a Dirichlet problem, or maybe a Neumann boundary condition, because I consider a lot of test functions. And so, for example, this is the Neumann boundary condition. Somehow that will become zero. So this is a very classical results that maybe can be found also. Most of this can be found in many textbooks, in particular the book of Brésis, the famous book of Brésis, I would say, which contains all these arguments and motivations, of course. So what we would like now to show, let me just show that what is known for this what is the regularity for the weak solutions. The known regularity are somehow, let me talk about existence because it will be important to parallel all of this in the non-local theory. When you in the non-local theory, so there are things. So I'm writing this because in the non-local case, you may have sometimes these inequalities or maybe this type of regularity, but sometimes you may not. And so this is the reason why I prefer to write all of this just to introduce what will come next. So the usual Poincaré inequality, maybe you all know that the gradient of the function is bounded by the square norm of the function, the L2 norm, if I am zero at the boundary, and with a constant which depends somehow in general on the measure of omega, and which of course blows up when the measure of the omega is becoming small and small. But at the same time, we also have the Poincaré inequality, which is sometimes called the Poincaré-Wirtinger inequality, in which case that the function should be perpendicular to 1, to the constant function 1. This is somehow important for the fractional Laplace, for the existence of solution in the Neumann problem. And of course, The constant function is in general a solution, so which means you have to kill it, or killing it in which way, which means you have to be perpendicular to the constant function in the L2 sense, which is exactly this. And yet these inequalities will just tell me that in fact I will be coercive when I'm looking at the minimization problem. I'm coercive, and so I can apply Lax-Milgram or maybe Riesz representation theorem or maybe any kind of argument that allows me minimizers. There are many arguments. And of course, anyone who is interested maybe can just look at the book of Brazis. Oh, no, sorry. My writing are very bad. I hope you can read it, but it's yeah, very strange. So let me. So the book of Brazis could be a very nice book to understand this. So, but all these arguments are very abstract. So in fact, in general, you only need a bilinear form, and then which is coercive continuous, and then you have solutions. And this is in general what happens for many things. So even if you replace the gradient with the gradient square norm with something else, in general, if you have this type of inequalities, which allows you to get a coercivity, then you get existence of minimizer. So which means even in the non-local theory, so it's still the same, and it doesn't cost too much somehow to obtain to obtain existence of solutions and things like that. So the classical regular theory. So let me just consider here the Dirichlet problem. So here, these are weak solutions. So if I have variational solutions for both the Dirichlet and the Neumann problem, I can immediately obtain many interesting arguments. So the first is that in fact I can have strong solutions. So in some textbooks they use the word strong solutions because when I have f in LP, then I can know that the fractional Laplacian of U or the fractional Laplacian of V, which is the solution to the Dirichlet or Neumann problem, they are pointwise defined. In fact, they are in LP. So, and in other textbooks also they call this the Calderon-Zygmunt theory. And you see, it's W2P, and when I consider W2P, so which means I have interesting things up to the boundary, and in fact, a simple implication I would say also is that if P is large, then in fact I am in C2 minus n over P up to the boundary. So which means also even my gradient is bounded and somehow up to the boundary, and even Holder continues. This is a result that can be obtained so maybe by using different arguments, maybe blow-up arguments, or maybe perturbative arguments, like Caffarelli, or many arguments can be used in order to prove this without knowing this. And of course, it's also, if you have, for instance, if omega is the full space, then one can also prove it by simply using the Riesz kernel. But in a sense, it comes directly by using the Morey embedding. memory embedding of the W2P in C2 minus N over P. And so, yeah, it's the immediate for classical theory. And now another interesting point is the Schauder theory. Sorry. So the Schauder theory in this case also for both solutions, we know that if I am Holder continuous, my right hand side is Holder continuous, and omega is Holder continuous C2 alpha, then my solutions are also C2 alpha. And this is important. And so the book for all these can be, so for all these results, so the book, the one of the best textbook is the Grisvard-Schrödinger. And so Grisvard-Schrödinger, so they use Fredholm theory in order to prove this, maximum principles and things like that, but still you can use Fredholm theory, which works perfectly for the Laplace operator. But when you come in the case of the fractional Laplacian, so there is a serious problem, and the Fredholm theory will not work. The reason is that, in a sense, so you cannot have this result. So it's impossible that you can obtain this. This is the main problem. This is the reason why, in a sense, one should somehow find out new techniques in order to obtain this regularity result. So the Fredholm theory is very interesting and also works nicely when you replace Laplacian with a divergence type operator or a non-divergence type operator, but it's non-clear. So the perturbative argument, or maybe the compactness argument, also in the spirit of Caffarelli, also works perfectly. So this is, and a blow-up argument also are nice enough, but sometimes it works, sometimes they do not work for the problems, for the non-local problems that will be considered. So the question now we are asking is maybe, okay, so here we simply consider weak solutions by looking at the H1, somehow energy space, the semi-norm of the energy space. But then if I look at, if I replace now the H1 Sobolev space by the HS Sobolev space for S smaller than 1, so what will happen? And we will see that even if I consider HS for S smaller than 1, this is the reason why I didn't put H1 omega and HS omega. Then even for S smaller than 1, there are many spaces. There are many spaces that approximate H1 0 and H1 omega, but which are both fractional and they have interesting similarities. So this is the reason why I just write H1 and HS, but instead of H1 omega and HS omega, and we will see the different spaces that can come into play, and also those spaces will define, as we should expect, the natural boundary condition, whether it will be Dirichlet, Neumann, or things like that. So the fractional Sobolev spaces. So the first, the fractional Sobolev spaces. So let me just look at. I just look at this, what we call, sometimes people call the Galliard norms, defined by the Galliard norms. But if omega is in Rn and even not an Rn, one can define them by Fourier transform. Maybe say the Bessel spaces and things, but still, if it's restricted on S between 0 and 1, it's simpler maybe to use the Galliard seminorm, because the use of these seminorms will allow us to see the operator under consideration. So the reference for this is the textbook of Grisvard, which contains all these, which contains many of these results. Even sometimes omega may not be considered Lipschitz, but even continuous also, in the results that I'm going to say below. So HS0, similar like H10, so is the smallest space that contains C infinity C in HS omega, and so well, one can think maybe that it had the same property than H1, but it's not the case. We will see that it doesn't have the same properties like H1, but even if it is defined by the closure of C infinity with respect to the HS norm, it's an interesting space, and in fact, and sometimes comparable to the HS space omega. Another interesting space is also the space calligraphic H, which is also the space HS0 calligraphic HS, which is the space of functions U in HSRN, but still U is 0 in the exterior of omega. And this space is endowed with respect to the norm HS. So in a sense, it's very interesting. So the norm HS, and somehow the Fourier transform notation works perfectly in this case. So the space calligraphic HS is different from the space HS0. And whenever you have a space, such kind of space, these are kind of Dirichlet space. They somehow define operators. And all the operators we will see, so they are different in a certain sense, and we will see that later. So there are interesting properties. So one of the first properties is the density. So if I remember, I think even omega Lipschitz is even too much, but even omega is continuous. I think you have C infinity C. Omega bar is dense in HS. Of course, by definition, we don't need to talk about. We don't need that. But so we have the density of C infinity C omega bar in HS. We also have a density of C infinity C in HS0 with respect to the HS norm, of course. With respect to the HS norm, which is true by weakening the regularity of omega, continuity is enough. And also, we have the link between the space HS0 and also the space HS. So if I wanted to be if I wanted to consider a function for which if I extend by 0, I will be in calligraphic H, because you know the calligraphic H as 0 are functions which are defined on Rn. So this is the reason why we consider the extension with tilde to be a function that is defined in Rn. But if I consider a function u which is in HS0, and if I extend it by 0, it is not necessarily in HS0 unless I ask this type of Hardy term to be finite. This type of Hardy terms, so these are scale invariant terms in the sense that it scales exactly like the semi-norm. And so it is not in fact negligible. But if you look at this carefully, then one can see that in fact the constant function, say the function 1, for s smaller than 1/2 belongs to hs0. So so if I look at this, so if 2s is smaller than 1, then the constant function 1 belongs to hs0. And also it satisfies which is so as a consequence, so if I extend the characteristic function, then belongs to hs0 omega. Calligraphic hs0. So this is a nice way somehow to find out whether certain functions also belongs to calligraphic hs omega. But if 2s is larger than 1, this is false. And so the link between the two spaces, so one can see that by just looking at the double integral. So if I look at the double integral, because hs0, so this is given by the hs norm in Rn. So if I look at the double integral, so sometimes if I write, so in Rn, integral Rn, then I can separate it, so with the semi-norm in omega squared plus the integral in omega integral in Rn minus omega. And so this is the semi-norm squared I don't know why something is the electricity. I think my hand has some electricity. Okay, so let me stop. So the semi-norm squared is given just by this. And so if I look at this, so I will have something like a u squared because somehow x, and I have the x minus y to the power n plus 2s. So the dx is for omega, and this guy is exactly when I look at this. So this term, so the integral over Rn minus omega. So this is the term that is somehow almost equal to the distance function to the x to the minus 2s. And this is the reason why one always have to find out this hard term. Another interesting fact which should comes is which we obtain is that the spaces hs0 and hs are the same for s between 0 and 1/2. So for s between strictly smaller than 1/2, it's not that difficult to prove. But for s equal 1/2, which is critical, it's not easy to prove. And so for this result, so one can look at the book of Grisvard and also, but it was where he quoted also the works of Jacques-Louis Lyons. And so this is already important to see, to show that, in fact, if I look at operators problems, variational problems that comes from these spaces, that there is something interesting, that if S between 0 and 1/2, I have an intersection of the Dirichlet and Neumann problem, which is yeah, it is somehow very strange. But the probabilistic people, they found out this, and they have a nice interpretation, which we will see very soon. So another property is that, in fact, we also have a trace theorem that if S is larger than 1/2, then I have the embedding. So I have a trace. So HF will have a trace, and of course, in fact, this is compact. Yeah. So this is a compact. Embedding, because I can be in HS minus 1/2, and this was stated in many books, but never proved. But Ding proved it in 1996 with a very clever argument. I think it was important, in fact, to write a proof instead of just quoting different papers in which maybe the proof are not very clear. Okay, so now I think we have all the spaces that we need in terms of if you are interested in the fractional, in the problems arising, problems involving the fractional Laplacian, or maybe regional fractional Laplacian. So what we always need in general is that the Sobolev inequalities, which also gives the provide embedding, and why I tell about this nonlinear inequality. So in general, this nonlinear inequality allows to run a de Giorgi iteration in order to obtain a priori L infinity bound and a priori Holder continuity and Harnack inequality. So one in general does not even need to get 2 star S, but so the scale invariant inequality, but simply a nonlinear inequality is in general enough. But the 2 star S norm is just sorry. So the 2 star S norm is just allows to obtain a scale invariant inequality, which is sometimes interesting for some applications. But when it comes to regularity estimates, one does only need a nonlinear inequality. So 2 star can be any p, but with p larger than 2. And of course, if 2s is larger than 1, then we can replace the semi-norm with the full norm. So in this case, that we also have the Sobolev inequality for role P between 1 and infinity, and which also provides a nonlinear inequality. And also in the case of a domain, so here it's not always true that you can just consider the semi-norm, but in most cases you need to consider the full norm. In some cases, the semi-norm does not bound from below, so we do not have only the inequality, even if we consider P, which is the scale invariant norm. But if you add the L2 norm, we always have a nonlinear inequality, which is in general enough for what one needs in the a priori bounds for weak solution. So maybe there are domains. So here, in a sense, one needs some kind of extension property domain which have extension property in order to use this inequality. But if omega is Lipschitz, it's fine. But there are open sets in which one does not have the inequality. That one does not have the Sobolev inequality, so which means one has to be very careful when one applies, or maybe think that this is an immediate consequence of the inequality that happens in Rn. So I think there are interesting books, but maybe the lecture note of Valdinocci and Palatucci, maybe this I think it contains interesting results. So let me see it. What's the folder? So the Hitchhiker's guide. So the Hitchhiker's guide contains in the section 5 this extension of Sobolev spaces, domains in which you can obtain the Sobolev inequality. But if omega is Lipschitz, we are completely safe. So I write here n minus 2s plus, which means that if n is smaller than 2s, then I can go up to infinity. So this is just to say that, or this is defined for n larger than 2s, but if n is smaller than 2s, I go up to infinity. Okay, so now I would like to introduce the problems that are involving the fractional Laplacian. So let me just introduce this energy. Sometimes one start with the problem and then look at the energy, but I do it in the other way around. I look at the energy and then I try to look at the Lagrange equation of the energy. But this is not the correct way. In general, the correct way, you have a problem and then you define your energy, the energy that you want to minimize. It is sometimes it's very easy to obtain the energy that has to be minimized and give you the Lagrange equation of the problem you want. But sometimes it's not immediate at all. But for the problem we are considering, this is not that difficult. And so here, this nice, this what is under consideration so if you look at in R2 and I look at omega here, so what I'm just looking at is the energy in the double energy in the spaces. And so this is the double energy in this space. And somehow, if you when you look at this energy, you can prescribe your Dirichlet problem with a non-zero Dirichlet problem. Of course, if you like, you can also prescribe a kind of exterior Neumann boundary condition. So the fractional Dirichlet problem. So if you wanted to fractional Dirichlet problem, so here you see I look at the calligraphic HS0. If I look at the calligraphic HS0, so this is exactly the semi-norm in HS Rn. of course, squared, 1/4. And so, because if you remember very well, the calligraphic HS0, which is different from HS0, is something that is defined on the whole space. It's a function that are defined on the whole space Rn, but even if they are zero at the boundary. In the case, now, if I leave the problem, if I leave the boundary free, which means I do not prescribe anything in the exterior, then in that case, I minimize among functions which are in HSRN, then both problems will become are different, but in a sense we can see this as the classical Dirichlet problem and the other one as a classical Neumann problem. And in fact, these are the case because if you look at the energy and if you send S to 1, recover the classical Dirichlet problem, which we introduced in the first slides, and also the Neumann problem as we introduced it in the first slides. But let us just look at the earlier Lagrange. So the derivative, the first derivative of the energy that we are considering. So here, if you look at this energy, then we simply see two terms that comes here. One is the integral in Rn, so the integral in Rn of ux minus uy, which is the fractional Laplacian, and another term which comes the fractional Laplacian and another term. So this is somehow a kind of, one can say it's a kind of counterpart of the Gauss-Green formula. But this just comes by using the symmetry of the kernel K. Xy is 1/mod x minus y to the power n plus 2s. And somehow this says that at least if I look at the minimizers for problem 1/12, in this case, I minimize and phi is infinity C function in omega, which means this is 0. And therefore this term disappears. However, if I let phi to vary in Rn, then I will obtain a kind of Neumann boundary condition, which was introduced by Di Piero, Ross Otton, and Valdenoch. And so, the consequence of this is precisely that we have the Poisson problem for, we have a Poisson problem which is brings the Dirichlet energy. So if I minimize, so my solution will become the Dirichlet problem, so with exterior Neumann boundary condition, and also a kind of Neumann boundary condition in the exterior. So these are the problems that the energy that I am considering so which is a non-local energy gives to me. So a Dirichlet problem, exterior Dirichlet problem, and a kind of exterior Neumann problem. And both problems, so if S is converging to 1, then we recover the classical problem, local problems. which means the Dirichlet problem for the Laplacian and the Neumann problem for the Laplacian. So this was introduced by Di Piero, Ross Ottens, and Valdinoch. Kind of exterior Neumann boundary condition. And it was since then, so it attracted many people. And in fact, there are interesting probabilistic interpretation. It was recently, I think it was Von Racek who also constructed processes related to this type of Neumann boundary condition, in which case somehow if particles are allowed to jump in the exterior of omega, but whenever they jump, so they are reflected again inside omega. In the Dirichlet case, this is very well known that in this case, so the process are killed when they leave omega. So in this case, you can think about the particles are allowed to jump in the exterior of omega, but whenever they are dead, so they are killed. Let me just say quickly that in the problems that we want to consider in this talk, which are the regional case, there particles will not be allowed to jump in the exterior. They can only jump inside omega, but they will never jump in the exterior. And this is so somehow they are censored to jump outside, and somehow they jump in a regional part, the regional under consideration, because the measure is killed. The measure is killed and is stopped. So in omega. So let me quickly discuss maybe few interesting properties for the fractional Laplacian. Is that if you look at the fractional Laplacian, so it's a pseudo-differential operator with a beautiful symbol, not differentiable at zero, but still nice to use. And of course, maybe you see maybe simply from here that if S is converging to 1, then you get the symbol of the Laplace operator. And we have interesting mapping properties that these are very important in general. So for instance, I mentioned in the beginning that sometimes one can use, for example, in the book of Gilbert Schrödinger, that one can use Prel'elmo theory to obtain also Schauder theory. So these are interesting properties that in fact allows you to do that, that your operator has some interesting mapping properties. So so just to mention that for the regional fractional Laplacian, this is not true, this is not true. So for the distributional domain of the operator, which is very important, is that in fact, so it's defined by the space L1S, which is the space of functions for which you have integrability far away at infinity. So, and this is this allows, in a sense, to say that in fact the fractional Laplacian acts on tamperic distribution. And this comes just from these estimates. In a sense, if we simply recall, so if you recall sometimes why this is not writing properly. Okay, so let me just stop. Okay, so if you recall if you recall the fractional Laplacian, then we see that if x is compactly supported, then far away we always have this term. So in a sense, this is not compactly supported. But anytime you have u in L1s, then the fractional Laplacian applied to u is a distribution. Wow. So the fractional Laplacian applied to u will become a distribution just because of this estimate. Well, in some work, several people, they try to enlarge this distributional domain. The distributional domain is, in a sense, maybe I would say the largest domain in which maybe when you can apply the fractional Laplacian on those functions. And there somehow they define a kind of equivalent class. So it's a paper of Di Piero, Valdinocci, and Savin by considering functions with polynomial growth. So when you look at functions with polynomial growth, of course, you know that if the polynomial, the growth of the polynomial is larger than 2s, then you cannot define the fractional Laplacian acting on those functions. But still, they find a way to define it. And in that case, so you have an equivalent class of solutions. So in a sense, when you act a function, when you act u on functions which have this type of growth, when you make the action of the fractional Laplacian of those functions, you have sometimes of this kind of growth, you can have many solutions, in fact, for the problems if you wanted to find solutions with polynomial growth. But it's an interesting fact that was used recently by Ross Otton and Abatangelo in order to obtain the optimal and full boundary regularity for the Dirichlet problem in the fractional Laplacian. So this is a paper that appeared recently in Advances of Mathematics in 2020. So another important factor is that, in fact, when you have a modifier, a nice modifier, then you can commute. You can commute the fractional Laplacian with modifier. So recall that the fractional, if functions that are here are temporary distributions, and therefore they have Fourier transform. In other words, so this can be proved using Fourier transform or simply using the symmetry of the integral. So it's a very nice thing to have, in a sense, maybe that you see if you have functions which are somehow harmonic or things like that, so you do not need to consider distributional solutions, but you can simply consider C-infinity solutions. You prove what you want to prove, and then you pass to the limit. You also have the Cato inequality. So the Cato inequality is sometimes useful also if you want to obtain decay or maybe bounds of solutions, and maybe one can prove the more general result. Maybe that let me try to write. So phi is Lipschitz and convex. So phi is Lipschitz and convex. Then one can also have the more general inequality, which is known as the Cato inequality, rather than only absolute value. And why this is interesting? Of course, this is interesting because somehow you can think about considering phi of t equal t to the power alpha. And therefore, with alpha larger than 1. And in this case, one can immediately think that with a nonlinear inequality, then I can run the de Moser iteration in order to obtain the a priori Holder estimate and Harnack inequalities. Yeah, so this is these are the in general the main ingredients that one needs. A nonlinear Sobolev inequalities and this kind of Kato inequality. So what all these results that I'm saying also, I just consider the fractional Laplacian, but it works for many other problems like replacing the kernel of the fractional Laplacian, but with a translation invariant kernel. But anytime you consider a translation invariant kernel, then in general you have all these properties. And therefore, one can just consider general non-local operators, and one can simply use the kind of de Giorgi iteration in order to get a priori bounds, because so you have Kato inequality and a nonlinear Sobolev inequality. So these are the questions. Well, I was also personally interested in is that maybe to find out explicit solutions that comes with the fractional Laplacian, and these are sometimes they are very rare, very difficult to get. And so what I was looking some years ago was that are there functions which are which are harmonic in the whole space with respect to the fractional Laplacian. So these are in the distributional sense. But as I said before, you may even consider UC infinity because convolution works perfectly. Because the operator commutes with convolution. And in a sense, when I was so trying to understand this, then I find out that in fact, as long as any time that I stay in the distributional domain of the fractional Laplacian, then there is no harmonic function which is not an affine function. And afterwards, so I used a proof, so by proving a kind of non-local Cauchy estimates. So from which I used them to prove this, but a nice proof or maybe a simple proof also can be used also, which uses precisely the Fourier transform. Because U is a temporary distribution because it is in L1S, and therefore you can simply consider the Fourier transform and invert the operator in order to obtain that. So the idea could be somehow that if I can make the Fourier transform, then I would say so the wow. Let me see. So if I look at the Fourier transform, then I will see that mod zeta to the power 2s u hat is 0, but mod zeta to the power 2s is different from 0 everywhere except at 0. So which means so the support of u hat is in 0. So this is formal proof. and from which this implies that in fact U is a polynomial. So this is a simple proof that can be used by Fourier transform, but of course to make the Fourier transform in this direction, so one has to do a little bit little works, but this is exactly the proof. And you know why? So this is not correct for the fractional for the Laplacian. Of course, for the Laplacian, the distributional domain is L1 log, and L1 log is not a temporary distribution. Therefore, you cannot use this argument. So so the argument that is used here is just because the fractional Laplacian acts on temporary distributions. So another rigidity result that were proved by Blumenthal and Gretor and Ray. So they computed the first the mean the expectation of the first exit time of the ball for the stable process that generates the fractional Laplacian. And in this case, they obtained that in fact the expectation of the first exit time is given precisely by this function u of x equal 1 minus mod x squared to the power s, and which this function solves exactly that this is constant 1 is in B1. The constant C is chosen is such the way that you have 1 here, and U is 0 in the exterior. And this function also provides also the boundary behavior of all solutions because it's like the distance function to the ball 1 minus mod x. So 1 minus mod x to the power s, so which is the distance function to the boundary. And this is the boundary behavior for solutions, which means one cannot expect, in general, better than this for solutions. So another rigidity result that was also proved by Wenxiang Cheng and co-authors also is that, in fact, on the half space, one can also classify all possible solutions is in the sense that if U is harmonic in the half space and 0 at the boundary, then it is proportional to xn to the power s, which is well. So you know, for example, if one is looking at the case of the Laplacian, this is somehow it is simply maybe one can make simply an odd reflection and maybe use the rigidity result on the whole space with spherical harmonics when you have a growth which is not big enough, because this growth makes a lot of restriction. So L1F provides growth, and this growth restricts that when you use the spherical harmonics, then you have polynomials, and all these polynomials will be killed except those that grows below L1S, so which means functions that grows below 2S. And this is the reason why you have all these restrictions, and this is the reason also why to construct you cannot have many functions. However, these restrictions are also kind of very bad, because if you want to prove a Holder regularity, maybe, or maybe the Schauder theory, you need CK plus alpha solutions. Somehow you need solutions which are C infinity somehow. But if you want solutions which are C infinity, but that means those solutions will have a Taylor expansion of polynomials of any order. And these functions are not in L1S. So this is the reason why it's in general difficult when you look at when you consider the fractional Laplacian operator, because sometimes when you blow up, you go out of the definition, the domain of definition of this of the Laplacian, of the fractional Laplacian, which is dangerous. And one way to overcome this is to differentiate all the time the solutions, or maybe to use this result of Di Piero, Savin, and Valdinocci on functions with polynomial growth. So in the case now of the Neumann boundary condition, so this is also in a classical thing that comes also for the Neumann problem. For the Neumann problem in general, so only affine functions which are tangent, affine functions which depend on the horizontal directions, solve the equations. And here we have the same for the Neumann boundary condition, exterior Neumann boundary condition, and we have only horizontal affine functions. Here you can see x prime, which also solve this equation, and one can check that this is true. And so a natural open question here is that, are these the only functions? Is it true that these are the only functions that solve this problem? So this is open questions is the converse. Is an interesting open question, because once you know that, then you can carry on a nice argument and somehow close up open problems that I will explain later, which means a kind of full regularity, bounded regularity for exterior Neumann problem. So converse, so this U is a solution, so the converse is open. Crazy. So the converse, I don't know what is going on. So the converse in any case is open. And so what I mean here by the converse is that, suppose that you have a solution U which solve 18, then is it true that U is of the form AX prime plus B? And there is no result about this, even in one dimension, nothing. So in one dimension, one should expect constant functions, but nothing is known about this. So further properties maybe that somehow allows, and which we will use. We will see that how they are important. Also, we will see also how they are important for the regional fractional Laplacian. Is all of these results. So because many of the things that comes for the fractional Laplacian, it comes for the regional fractional Laplacian. But we have more hours to discuss this in the coming lectures. So the wing maximum principle is rather easy to prove. that if you have just a function u, so which is in hs0, hs0 also can be decreased by can be weakened. So here, so can be weakened by considering something more, maybe can be weakened by considering something u is classical solution, but maybe what is simpler, maybe u is continuous, or lower semi-continuous in omega and in L1s. Oops, sorry, what's happening here? Very strange. Sorry for this. I don't know what is happening for the pen, but anyway. So if u is in L1s and it is continuous, then you also have the solution that continues up to the boundary, of course, or lower semi-continuous. Then you also have the weak maximum principle. And the strong maximum principle, or maybe the Hopf lemma, comes also with in the sense that if I have a solution also which is continuous, I can also weaken h as 0. Then either u is equal to 0, or I am larger than the distance function to the boundary to the power s, which is the optimal regularity that we mentioned before. And this is somehow the Hopf lemma, but not here that we have the Hopf lemma, but in the classical theory, the Hopf lemma, in fact, will tell us how that whether the function is increasing or decreasing from the boundary. But you know, this Hopf lemma does not tell that. And of course, in order to reach the gradient, or maybe to see somehow the monotonicity of u, one need further estimate which is sometimes important to have. And this is an interesting open problem in my opinion, that even if I have u, which is C1, sorry, which is somehow continuous up to the boundary, and C1 locally C1, then do I know whether the solution is somehow monotone from the boundary or not? So this is something that is, I think, very important. So in some cases it's true, and this is proved recently. So in the paper, but for I would say eigenfunctions, and this is true. This is proved in the recent paper with Steven Yaros and myself, where a weighted gradient is well defined and have the same sign like u over distance function. And in this case, we have, even if the gradient blows up at the boundary, but you still have the sign. So it converts to plus infinity, but you still have a sign, and this tells about the monotonicity of the solutions. So I'll just stop here after this slide, and then we will start maybe the next lecture with the regional fractional Laplacian, and perhaps we'll become more technical in the proofs. So these results are known results, of course, since many years ago, but there are modern proofs also in many papers of Sylvestre and papers of Ross Otten and Serra, so which provides the interior Holder regularity. And also, this is also known since many years, that in fact we have strong solutions in the interior, but the boundary is in general very strange. And so what is known with the optimal regime, so this is recently proved by Abbott-Angelo and Ross Otten, is in fact that in fact, you can have, if omega, so the optimality is with respect to omega, of course, because if omega is infinity, this was known from graph. And somehow, if f is c alpha, then you have the function over the distance function is cs plus alpha. And so sometimes you can think about this, that this is, you multiply delta s with the cs plus alpha, and you can think about, you almost have like 2s plus alpha. So this was open. In fact, the optimal regularity that is needed for the boundary in order to get this, and this was resolved recently by Rosaton and Serra and Abatencello. Oh, sorry. So this is a result somehow of graph. Sorry. So this is SP. So this is. So let me consider this. This is not part. So this is HSP. I'm sorry here. So this is the LP theory for the fractional Laplacian, and we are very different from W to SP. In fact, you cannot have the solution cannot be in W to SP. There are counterexamples. In fact, the explicit solutions for the ball show that you can never have W to SP. And all these results are optimal, but except that in this case, so the regularity assumption on the boundary, the optimality is still open. So this was proved by Grubb, first for omega is infinity, and Grubb and Helmut Abel for in the case where the omega is holder is C1 beta, but for some beta which is not optimal. So the question that may be natural ask is what also happened in the Neumann case. In the Neumann case, what is known, this is very recent. And so for now, the only known regularity in the Neumann case is that in fact the solution is 2s minus 1 plus alpha for some alpha positive. So and all the rest is open. And this is a result that was proved. Oops, sorry. That was proved by Ross Orton and several and different authors. So the only result that you know is 2s minus 1 plus alpha. And of course, one should expect more than this, in my opinion, but this will come when one can prove the rigidity result, namely the classification of the solutions in the half space. Then I think that would be a very good step in order to see that one should in fact obtain more than 2s minus 1 plus alpha. This is really not optimal. And so the natural questions that we are going to ask and that we will discuss are whether these results are true for the regional fractional Laplacians or not. As we will see that in fact there are almost no results, very, very few, maybe 2 papers dealing with the boundary regularity for regional fractional Laplacian. And these are the papers, these are the results that I'm going to talk about in the coming lectures. And perhaps we will be a bit more technical and talk about a little bit the proofs. Not deeply, of course, but we will just sketch some proofs. But in any case, what we want will be that to discuss about what will happen in the case where we replace the fractional Laplacian with the regional fractional Laplacian. So I will probably stop here for today and maybe leave the remaining time for discussions.
Okay, Thank you, Professor Fall, for the very interesting lecture. Some question or comments?
May I ask one question? I mean, there is this. No, my question is about W2 quelque chose regularity. I mean, W2 just W2 something. So my question is, there is this paper by Hu Yu from Columbia, and I think the paper the results some sort of Feng Hualing estimate for non-local problems. So my question is there any clear bottleneck or clear obstacle to move from this W2 delta to something like W2P or W2D or something like this, as in the usual W2P Caffarelli regularity theory?
Yes, in fact, there is a kind of W, I would say TP regularity, of course. So TP omega itself, but with T, so one is what knows is, for example, if F is in L2, then you are in somehow H, or maybe W is the same because it's S plus 1/2 minus epsilon 2. So 1S plus 1/2 minus epsilon omega. So in a sense, and this is 1/2 minus epsilon is kind of optimal because of the explicit solutions that you can get when you consider a ball.
Okay, let's see.
Did I answer your question? Or?
Yes. Yes.
Okay.
Thank you. Thank you.
Some more question or comments? I have one. Is maybe it's naive, but the solution you talk about weak solution, but all the results holds for viscous solution. All the results that you talked.
Yes, of course. Many of them are true for viscosity solutions. For instance, I think even Ross and Sarah, for them, they use viscosity solutions. Grupp doesn't use viscosity solutions. So it depends. It depends on the authors. But in fact, I think one interesting question, which is studied, I think, by Bukur and co-author, is to go sometimes when you have viscosity solution, is it a weak solution and things like that. So to moving from viscosity to weak solutions. But the proofs, for example, the results, in fact, in general, works for both of them. But it depends. For some, from author to author, some they just completely consider viscosity solution.
Okay. Okay. Thank you. Some more comment or question? Okay, then we met again Wednesday at 9. Thank you, Professor Fall. See you later.
Okay, at 9, 12 in our case. So 9 plus 3.
Hey. Yeah. 10 plus 3.
Yeah,
Bye.